Before sunrise, while almost everyone along the Oregon and Northern California coast was asleep, the ocean floor moved. There was no flash in the sky, no siren, no wall of water racing toward shore, no breaking news banner cutting into television screens. Just a silent pulse from deep beneath the Pacific, traveling through stone faster than any human warning could ever move. At 2:53 in the morning Pacific time, far offshore west of the Oregon coast, a magnitude 5.7 earthquake struck beneath the seafloor. On land, most people felt nothing. In the small towns along Highway 101, people kept sleeping. Fishing boats stayed tied to the docks. The dark beaches stayed empty. The forests above the coast did not shake apart. No buildings fell. No power lines snapped. No emergency crews rushed into the streets. And that is exactly why most people missed the real story. Because the important part of this earthquake was not what it destroyed. It destroyed nothing. The important part was where it happened. It happened near one of the most dangerous geological corners in North America, a place where the Pacific Plate, the North American Plate, and the small broken Gorda Plate all meet in a violent, complicated collision zone beneath the ocean, a place where the Cascadia subduction zone ends, a place where the San Andreas system begins, a place where the Earth does not behave cleanly, smoothly, or predictably. And within hours of that first offshore quake, more earthquakes appeared farther south near the Northern California coast. One dot on the map became several. One offshore pulse became a cluster. No tsunami warning was issued. No major damage was reported. And to be absolutely clear from the beginning, this does not mean the big one is starting. The data does not say that. But the data does say something more subtle and maybe more unsettling. It says that the same tectonic neighborhood that will one day be involved in the next major West Coast earthquake just moved again before dawn, quietly, without damage, without attention, and without giving anyone a clear answer about what comes next. That is the uncomfortable part, because earthquakes like this usually fade into the background. Most of the time, they are just another entry in the USGS catalog. A small cluster, a routine offshore sequence. A few hundred "did you feel it?" reports. A few local news articles. Then silence. But every major earthquake in history also began as something ordinary, a fault that had been locked for centuries, a section of crust that had been taking stress for generations, a quiet morning, a few numbers on a screen. And then suddenly the world changed. Tonight we are not going to turn this into fear. We are not going to claim that a catastrophic Cascadia rupture is hours away. That would be dishonest. But we are also not going to dismiss it as nothing, because this is the kind of event that lives in the grey zone between normal and meaningful. Between routine activity and possible warning, between the science we understand and the part of the Earth we still cannot predict. So in this video, we are going to walk through what happened, why the location matters more than the magnitude, why the Gorda Plate is the hidden character in this story, why the main Cascadia fault did not appear to be the one that moved, and why scientists still pay attention when this particular corner of the Pacific begins to crack. By the end, you will understand why a quiet offshore earthquake that caused no damage can still matter. You will understand why the West Coast sits beside a clock no one knows how to read, and you will understand why the most honest sentence about this morning is also the most unsettling one. This was probably nothing, but it was not nothing. In Chapter 1, the Earth moved while everyone was asleep. At 2:53 in the morning, the coast was dark. The Pacific was black. From southern Oregon down into northern California, the small towns along the edge of the continent were quiet in the way only coastal towns are quiet before sunrise. Brookings was asleep, Crescent City was asleep, Eureka was mostly asleep. Highway 101, the road that follows the edge of the Pacific like a thin human line drawn beside something much older, had only a few headlights moving through the darkness. Out beyond the beaches, beyond the fishing boats, beyond the last lights of shore, the ocean floor was under pressure. Not sudden pressure, ancient pressure. The kind that builds year after year, century after century, so slowly that human beings almost cannot feel it until the moment it breaks. Then, deep beneath the seafloor, a fault slipped. The rupture was not large by global standards. It was not a magnitude 8. It was not a magnitude 9. It was not the kind of earthquake that rewrites maps. But it was strong enough to send seismic waves racing through the crust in every direction. The first waves moved fastest. These are called P waves, pressure waves, the first signal that something has gone wrong deep underground. They move through rock like sound moves through air, compressing and expanding the material as they travel. Within seconds, those waves were moving toward the coast. Within less than a minute, they reached instruments on land. A seismometer felt it before any person knew anything had happened. Then another station felt it. Then another. Then the automated earthquake systems began doing what they do every day, silently and with incredible speed. They measured the arrival times. They compared the signals. They calculated a location. They estimated a depth. They assigned a magnitude. And before most people in the region had even turned over in bed, a new dot appeared on the earthquake map. Magnitude 5.7, offshore Oregon, far enough from land that the shaking would be weak for most people. Close enough to the tectonic boundary that seismologists would notice immediately. That is the strange thing about this kind of earthquake. For the public, it can feel like almost nothing. For the instruments, it is unmistakable. And for the scientists who know this region, the location is impossible to ignore. Because this was not just somewhere in the Pacific. It was not random ocean. It was not an isolated crack in an empty place. It happened near the southern end of the Cascadia subduction zone, near the Mendocino Triple Junction, near the place where multiple plate boundaries collide in a small and violently complicated zone beneath the sea. And then, after the first quake, the morning did not immediately go quiet. More dots appeared. Farther south, off Northern California, another earthquake struck. Then another. Then another. The magnitudes were smaller than the first one, but they were not meaningless. They were large enough to show that this was not a single isolated tick in the system. It was a cluster, a short pulse of activity in one of the most closely watched tectonic neighborhoods on the West Coast. And yet, on land, life barely changed. That contrast is the first thing you have to understand. The Earth moved. The instruments recorded it. The tectonic system briefly spoke. But the human world barely heard it. No major emergency response followed. No tsunami warning went out. No coastal evacuation was ordered. No bridges cracked. No hospitals filled with injured people. No dramatic footage appeared online because there was nothing dramatic to film. That is why events like this vanish so quickly from public attention. A major earthquake in a city becomes a story because cameras can see it. A moderate earthquake offshore becomes a line of text. Magnitude, depth, latitude, longitude, time. But geology does not care whether a camera is present. It does not care whether an event becomes a headline. It does not care whether people were awake when the crust moved. And sometimes the most important events are not the ones that look dramatic from the surface. Sometimes the important events are the ones that appear quietly on a technical map while the rest of the world is asleep. That is what happened here. The first event was not catastrophic. It was not even especially rare for this region. But it happened in the right neighborhood, at the right depth range, inside the right kind of tectonic system, at the right moment in Cascadia's long, quiet cycle to make people who watch this region stop and look twice. And that is the beginning of the story. Not panic, not certainty, attention. Because the question after a morning like this is not, did the big one begin? The answer to that, based on the public data, is no. The better question is this. If the big one ever did begin with a whisper, would anyone recognize it before the shout? That is why we keep going. Chapter 2. Why a 5.7 can be bigger than it sounds. A magnitude 5.7 earthquake sits in a strange place in the public imagination. It is big enough to sound serious, but not big enough to instantly terrify people. When most people hear magnitude 5.7, they do not think of catastrophe. They think of shaking lamps, rattling windows, a few cracked walls, maybe a nervous local news report. And depending on where it happens, that can be accurate. A 5.7 under a city can be damaging. A 5.7 far offshore can pass almost unnoticed. The number alone does not tell the whole story. Magnitude is only one part of an earthquake's identity. Location matters. Depth matters. Fault type matters. Distance from people matters. The kind of rock the waves travel through matters. The direction of the rupture matters. And most importantly for this story, the tectonic neighborhood matters. That is why this earthquake deserves more attention than a simple headline gives it. If the same magnitude 5.7 had happened in the middle of an empty desert, far from any major fault system, it might be interesting but not especially meaningful. If it had happened in a known aftershock zone following a recent larger earthquake, scientists might treat it as part of a normal decay pattern. But this one happened offshore near the southern Cascadia system, near the Mendocino Triple Junction, in a region where the Earth is already under complicated stress from multiple directions. That changes the meaning. Not because a 5.7 is dangerous by itself, but because it happened in a place where small movements are part of a much larger machine. Think of it like hearing a noise inside a building. If you hear a single crack in an old wooden chair, you may ignore it. If you hear the same crack inside a dam holding back a reservoir, you listen differently. The sound may still mean nothing, but the structure around it changes the stakes. That is how we should think about this earthquake. The magnitude was moderate. The damage was basically absent. The tsunami risk was not significant, but the location put it inside a much larger question. And that larger question is Cascadia. The Cascadia subduction zone is one of the most dangerous faults in North America, not because it produces frequent disasters, but because it can remain quiet for centuries before producing an enormous one. It is a locked boundary where oceanic crust is being forced beneath the North American continent. Year after year, the plates keep moving, but parts of the fault do not slip smoothly. They stick, they lock, they bend the crust, they store energy, and one day that stored energy will release. That is not speculation. That is the basic physics of the system. The uncertainty is not whether Cascadia can rupture. It has ruptured before. The uncertainty is when it will rupture again, how much of the margin will break, and whether there will be any recognizable warning before it happens. That is why a moderate earthquake near the southern end of the system matters, not because it proves anything. It does not, but because it reminds us that the entire region is alive with stress. Most earthquakes in this zone are not the big one. Most are routine. Most do not lead to anything larger. But the big one, whenever it comes, will not arrive from a different planet. It will come from this same system, this same boundary, this same long, restless edge of the continent. That is what makes the situation so difficult to talk about, honestly. If you exaggerate, you create panic. If you dismiss it, you create complacency. The truth is in between. A 5.7 offshore Oregon is not a disaster. But it is also not meaningless when it happens beside one of the most consequential locked faults in the United States. And there is another reason the magnitude can be misleading. Earthquake size grows logarithmically. That means each whole number increase in magnitude represents a much larger release of energy. A magnitude 6 is far stronger than a magnitude 5. A magnitude 7 is far stronger than a magnitude 6. A magnitude 9 is not just a little bigger than a 5.7. It is in a completely different category of planetary violence. So we need to be careful. This offshore quake was not close to Cascadia's worst-case size. It was not a preview of magnitude 9 shaking. It was not a mini version of the big one. But it occurred inside the region that is capable of producing that kind of event. That is the distinction, and it is the distinction most short news reports miss. They tell you the number. They tell you the location. They tell you no tsunami warning was issued. Then they move on, but they rarely explain why that location matters. They rarely explain the broken plate beneath the ocean. They rarely explain the triple junction. They rarely explain the 326-year clock running beside the coastline. They rarely explain why scientists can say, at the same time, this is probably routine, and this is still worth watching. That is what this video is here to do, because the number was not the warning. The address was. Chapter 3. The map. Nobody on the news explains. To understand why this earthquake matters, you have to stop looking at the normal map. Forget state borders for a moment. Forget counties. Forget highways. Forget the neat coastline drawn on weather graphics and tourist brochures. That map is useful for people. It is not the map the Earth uses. The Earth has another map beneath it. A map of plates. A map of boundaries. A map of locked faults, spreading ridges, transform zones, fracture lines, and slabs of oceanic crust being forced downward into the mantle. On the human map, the earthquake happened offshore Oregon and Northern California. On the tectonic map, it happened near a collision zone where 3 major pieces of the Earth's outer shell are interacting at once. That is the real map. And once you see it, the west coast looks very different. Start north. Off the coast of British Columbia, Washington and Oregon, an oceanic plate is moving toward North America. It is not moving fast in human terms. Only a few centimeters per year. About the speed your fingernails grow. But the Earth has time. A few centimeters per year becomes meters over a human lifetime. It becomes kilometers over geological time. And when a dense oceanic plate meets a continent, it does not simply stop. It dives. It slides beneath the lighter continental crust and begins descending into the mantle. That process is called subduction. And the great fault created by that process is the Cascadia subduction zone. Cascadia runs for roughly 1,000 kilometers from Northern California up past Oregon and Washington toward Vancouver Island. For most of that distance, the story is fairly clean. Oceanic plate goes down. North America rides above. The boundary between them locks, loads, and sometimes ruptures. But then you reach the southern end. Near Cape Mendocino, the clean story breaks apart. Cascadia does not simply continue south forever. Instead, the subduction zone ends. And south of that point, the plate boundary becomes something else entirely. The San Andreas system, that is a transform boundary where the Pacific plate and North American plate slide past one another horizontally. So just offshore Northern California, the entire character of the West Coast plate boundary changes. North of the corner, one plate dives beneath another. South of the corner, plates slide sideways. And right at the transition is a zone of severe geological complexity. This is the Mendocino Triple Junction. It is not just a point on a map. It is a tectonic knot, a place where the Pacific Plate, the North American Plate, and the Gorda Plate all meet. And each one is doing something different. The Pacific Plate is moving northwest. The North American Plate is moving relative to it in a different direction. The Gorda Plate is being squeezed, cracked, and pushed beneath the continent. That small Gorda Plate is the key. Because when people talk about the West Coast, they usually talk about two names: Cascadia, San Andreas. Those are the famous threats. Those are the names that appear in documentaries, emergency planning documents, and disaster scenarios. But between those two famous systems sits a less famous piece of crust that absorbs incredible stress: the Gorda Plate. It is small compared with the major plates. It is broken. It is internally deformed. It is under pressure from multiple directions. And it produces earthquakes again and again because it is not moving as one clean, solid block. It is cracking within itself. That is why the map matters. If you look only at the coastline, the June 3 sequence looks like a handful of offshore quakes. Interesting, but not extraordinary. If you look at the tectonic map, those dots appear near the southern edge of Cascadia, near the northern reach of the San Andreas system, near the zone where the Gorda Plate is being crushed and consumed. Suddenly, those dots are not random. They are part of a larger mechanical setting. Again, that does not mean disaster is imminent. It means the location deserves respect. Imagine standing in a house and hearing a noise in the walls. If the house is new, stable, and quiet, maybe the noise means nothing. But if you know the house sits on a slope, has a cracked foundation, and has shifted before, the same noise gets your attention. The West Coast is that house. The crack in the wall this time was offshore. Most people did not hear it, but the instruments did. And the instruments placed it in a neighborhood that has shaped the entire seismic history of the Pacific Northwest. This is why simple news coverage is not enough. A headline can tell you there was an earthquake. It cannot tell you the story of the boundary beneath it. It cannot show you how Cascadia ends. It cannot show you how San Andreas begins. It cannot show you how the small Gorda Plate is caught between forces larger than itself. And without that map, the event looks smaller than it really is. Not because the magnitude was huge. It was not. But because the system around it is huge. The hidden map is the story. And on that map, the earthquake happened in one of the most important corners in North America. Chapter 4. The corner where three plates collide. There are places on Earth where geology is simple enough to explain in one sentence. This is not one of them. The Mendocino Triple Junction is not simple. It is not clean. It is not a single fault line drawn neatly across the ocean floor. It is a crowded intersection where enormous pieces of the planet meet, grind, dive, slide, and deform at the same time. If you want to understand why scientists pay attention to earthquakes here, you have to understand the violence of that geometry. Three plates meet here: the Pacific Plate, the North American Plate, and the Gorda Plate. Each one is moving. Each one is pushing or sliding against the others, and the forces do not line up neatly. That is what makes the region so restless. The Pacific Plate is the giant. It makes up much of the floor of the Pacific Ocean. It is one of the largest tectonic plates on Earth. The North American Plate is the continent. It carries the western United States, Canada, and much more. Then there is the Gorda Plate. Small, fractured, squeezed, easy to overlook. But in this story, it may be the most important character. The Gorda Plate sits offshore of southern Oregon and northern California. It is a remnant of an ancient plate system, a surviving fragment of a much larger oceanic plate that has been mostly swallowed beneath North America over tens of millions of years. And today, that small remnant is caught in a brutal position. To the east, it is being forced beneath North America as part of the Cascadia system. To the west, new crust is being created at a spreading ridge. To the south, it interacts with the Pacific Plate along fracture zones. To the north, it connects with the broader Juan de Fuca system. It is being born, squeezed, broken, and consumed all at once. That is why the Gorda Plate does not behave like a calm slab of rock. It behaves like a damaged piece of glass under pressure. Push gently on a solid tile and it may hold. Push on a tile that is already cracked from three sides, and the cracks begin to talk to each other. One edge slips, another edge adjusts. A hidden fracture opens slightly. A tiny piece grinds against another. That is what the Gorda Plate does. It produces frequent earthquakes, not because something unusual is always happening, but because the plate itself is internally damaged. The earthquakes are the sound of that damage continuing. Most of them are small, some are moderate. Occasionally, larger events occur, and because the plate sits beside Cascadia, every pulse of activity in this zone raises the same question. Is this just the broken plate adjusting, or is it somehow connected to the larger locked fault nearby? That question is not easy to answer in real time. It is also not a question honest scientists can ignore. The Mendocino Triple Junction is important because it is a meeting point between different earthquake worlds. North of it lies the subduction world of Cascadia. That is the world of megathrust earthquakes, vertical seafloor movement, coastal subsidence, and tsunamis. South of it lies the transform world of the San Andreas. That is the world of horizontal strike-slip motion, violent shaking, and long ruptures running through California. Inside and around it lies the broken world of the Gorda Plate. That is the world of internal deformation, offshore clusters, complicated faulting, and constant background seismicity. The June 3 sequence happened in this third world, the broken world, but it happened close enough to the other two that it cannot be completely separated from them. That is why the event is scientifically interesting, even if it was not publicly dramatic. A small earthquake in a quiet region is one thing. A moderate cluster in a tectonic triple junction is another. The triple junction is already one of the most active seismic zones on the west coast. It produces earthquakes frequently. That fact cuts both ways. On one hand, frequent earthquakes mean this latest sequence may be normal. It may simply be another pulse in a chronically active region. That is the most likely interpretation. On the other hand, because the region is so active and so structurally connected, scientists have to watch how sequences evolve. Do they fade? Do they migrate? Do they increase? Do they trigger nearby structures? Do they remain inside the Gorda Plate, or do they begin to involve the major boundary faults? Most of the time, the answer is simple. They fade. The cluster ends. The catalogue returns to background. Nothing larger happens. But the fact that most sequences fade does not make the location irrelevant. It only means the Earth gives many small reminders before it gives a major one. And the difficult part is that before the major one happens, people may not know which reminder mattered. That is why this corner matters so much. The Mendocino Triple Junction is not famous like San Andreas. It is not feared by the public like Cascadia, but it is the place where those worlds come close together. It is the hinge between the Pacific Northwest's greatest earthquake threat and California's most famous fault system. It is the place where the West Coast changes its tectonic language. And on June 3, before sunrise, that hinge moved again. Not catastrophically, not clearly as a warning, but enough to remind anyone watching the hidden map that the corner is still active. The plates are still moving, the stress is still there, and the clock beneath the coast has not stopped. Chapter 5. The Gorda Plate, the broken piece beneath the ocean. Most people have never heard of the Gorda Plate. That is understandable. It does not have the fame of the San Andreas Fault. It does not have the disaster mythology of Cascadia. It does not run under major cities in a way that makes it easy to imagine. It sits offshore, mostly hidden beneath cold Pacific water, far from cameras and traffic and buildings. But if you want to understand what happened during this earthquake sequence, the Gorda Plate is where the story really begins. Because this plate is not just a passive piece of ocean floor. It is one of the most stressed, fractured, and internally restless pieces of crust on the western edge of North America. It is small, but small does not mean calm. In fact, its small size is part of the problem. Large tectonic plates can behave like massive rigid blocks over huge distances. They bend, yes. They deform, yes, but they can distribute stress across enormous areas. The Gorda Plate does not have that luxury. It is compact, trapped, and squeezed. It is caught between the Pacific Plate, the North American Plate, the spreading ridge that creates new oceanic crust, and the subduction zone that destroys it. It is like a small piece of metal caught inside a machine that is still running. Every side is moving, every boundary is applying force, and because the forces are not perfectly aligned, the plate cracks inside itself. This is why earthquakes inside the Gorda Plate are so common. They are not all happening on one clean master fault. They happen across a network of internal breaks. Some faults trend roughly north to south, others trend more east to west. Some are related to the spreading structure offshore. Others are related to compression, rotation, or shearing inside the plate as it approaches the subduction zone. The result is messy, and messy geology produces messy earthquake patterns, clusters, swarms, moderate events, depth uncertainty, fault mechanisms that take time to refine, multiple agencies reporting slightly different values in the first hours after an event. All of that is normal in a place like this, but normal does not mean unimportant. The Gorda Plate matters because it sits directly beside the southern Cascadia system. The oceanic crust that forms offshore eventually moves east and is forced beneath North America. As it approaches the coast, it does not glide smoothly into the subduction zone like a clean conveyor belt. It arrives already damaged, already cracked, already internally stressed. That matters because the condition of the subducting plate affects the whole system. The Gorda plate is not the main locked Cascadia fault, but it is part of the machinery that loads it. This is where many people get confused. They hear earthquake near Cascadia and assume it happened on Cascadia. That is not necessarily true. A quake can happen near the Cascadia subduction zone without happening on the main megathrust interface. It can happen inside the Gorda plate. It can happen on a transform structure. It can happen on a fracture zone. It can happen in the surrounding system rather than on the locked fault itself. That appears to be the key distinction with this sequence. The dangerous Cascadia megathrust, the fault capable of producing a magnitude 9 event, does not appear to be the structure that ruptured in this sequence. That is good news. Very good news. Because an internal Gorda plate earthquake of moderate size is not the same thing as a Cascadia megathrust rupture. It cannot simply become a full margin Cascadia rupture in the way people might imagine. The geometry is different. The fault type is different. The scale is different. The physical structure is different. But, and this is the part that keeps the story interesting, nearby faults can still influence each other, not like dominoes falling in a straight line, not like one earthquake automatically triggering the next, but through stress changes. When one fault slips, the stress in the surrounding crust changes slightly. Some areas are relieved, other areas are loaded. Most of the time, the change is too small to matter. But if a nearby fault is already close to failure, a small change can sometimes advance the timing. This is why the Gorda plate is such an important character. It is not the villain. It is not proof of imminent catastrophe. It is the restless neighbor beside the locked door. The locked door is Cascadia. The Gorda plate is the cracked floor in front of it. Most of the time, the cracked floor shifts and nothing happens to the door. But if the whole building is under stress, you still notice when the floor moves. That is the correct way to think about this sequence. A moderate earthquake inside the Gorda plate is not a Cascadia rupture. It is not the big one. It is not a tsunami-generating megathrust event. But it is movement inside the larger system that surrounds the fault everyone is watching. And because the Gorda plate has been deforming for millions of years, this is not a one-time event. It will keep happening. The plate will keep cracking. It will keep producing offshore earthquakes. Most will be forgotten. Some will be studied. A few will become part of larger sequences. And one day, whether related to a visible foreshock sequence or not, the Cascadia system itself will release. When that happens, the Gorda plate will not be a footnote. It will be part of the story, because the southern end of Cascadia is not a clean, quiet boundary. It is a broken, crowded, restless place where plates meet under enormous pressure. That is why this earthquake sequence matters. Not because it proves the big one is near, but because it came from the broken piece of earth sitting beside the fault that cannot stay locked forever. Chapter 6. What actually happened in the sequence. Now let's slow down and look at the sequence itself. Because in the first hours after an offshore earthquake, information can look confusing. One agency reports one magnitude. Another agency reports a slightly different magnitude. Depths change. Locations adjust. Social media posts begin spreading screenshots before the official solutions have been reviewed. And suddenly, ordinary uncertainty in early earthquake data starts looking mysterious to people who do not know how these systems work. There is nothing mysterious about that. Earthquake reporting is fast, but it is not instantly perfect. The first numbers are not final answers. They are rapid estimates. They are the first draft of the event. Here is the basic timeline. The first major event struck offshore west of the Oregon coast in the early morning hours. The magnitude was reported around 5.7. The depth was around the typical shallow to mid-crustal range for this offshore region, roughly around 10 kilometers in the early public reporting. That first event was the largest in the sequence. It sent waves through the crust and into the seismic network along the coast. Land-based instruments picked it up quickly. Automated systems calculated the location and pushed the information into public feeds. Then, within the same broad morning window, additional earthquakes appeared farther south, offshore Northern California, near the region of Petrolia and the Mendocino Triple Junction. These later events were smaller than the first. Some were in the magnitude 4 to 5 range. They occurred near the same broad tectonic corner, but not necessarily on the exact same fault. That is important. When people see several earthquakes close together on a map, they often imagine one crack opening like a zipper. But earthquake clusters do not always work that way. Sometimes they are aftershocks on the same structure. Sometimes they are separate faults responding to the same regional stress field. Sometimes one event slightly changes stress enough to encourage motion nearby. Sometimes the timing is partly coincidental inside an already active region. The map alone cannot tell you which one is true. That is why seismologists need more than dots. They need waveforms. They need focal mechanisms. They need refined depths. They need aftershock patterns. They need time. and that is especially true offshore. On land, earthquake networks can surround an event with instruments. Stations can be north, south, east, west, close to the source, far from the source, and at many different angles. That helps locate an earthquake more precisely, but offshore events are harder. Most instruments are on land. The earthquake happens under the ocean. That means the seismic network is not perfectly wrapped around the source. It is mostly on one side of it. Imagine trying to locate a sound in a dark room when all your microphones are placed along only one wall. You can still estimate where the sound came from, but some details, especially depth, become harder to pin down immediately. This is why early offshore earthquake depths sometimes shift after review. An initial automatic solution may place an event very shallow. Later analysis may move it deeper. That does not mean anyone is hiding something. It does not mean the earthquake changed. It means the estimate improved. This matters because online misinformation often grows in the gap between the first automatic estimate and the final reviewed solution. Someone sees a strange depth. Someone sees different agencies reporting slightly different values. Someone notices a revision. Then a theory appears. But revisions are part of the process. They are not evidence of deception. They are evidence that the system is being refined. For this sequence, the most important fact is not whether one event ends up being listed as 5.6 or 5.7, or whether a depth estimate shifts by several kilometers. Those details matter scientifically, but they do not change the main story. The main story is that a moderate offshore earthquake occurred near the southern Cascadia-Gorda-Mendocino system, followed by additional moderate activity farther south in the same broader tectonic region. The largest event came first. The later events were smaller. That pattern matters. Because if this were a classic escalating foreshock sequence, one thing scientists might look for is acceleration. More events, larger events, events getting closer together, events migrating toward a future rupture area. But in the early public data, this sequence looked more like a moderate main shock followed by smaller related activity than a clean build-up towards something larger. That is reassuring, not conclusive, but reassuring. The Earth does not always follow textbook patterns, and many foreshocks are only identified after a larger event happens. But based on what was visible in the first stage, the sequence did not scream imminent catastrophe. It looked like a pulse. A strong, interesting pulse in a very active region. That is why the responsible interpretation is balanced. The sequence is not something to ignore, but it is also not something to inflate. It deserves attention because of where it happened. It does not justify panic because of what it did, and what it did was limited. The earthquakes were offshore. Shaking on land was generally light. No major damage was reported. No tsunami warning was required. The public impact was minimal, but the scientific meaning was larger than the public impact. That is the central tension of this whole story. For the people living on the coast, the morning may have felt ordinary. For the instruments, it was a clear seismic sequence. For scientists, it was another reminder that the southern Cascadia region is not quiet because the system is dead. It is quiet because much of the most dangerous fault remains locked. Around that locked fault, the rest of the system continues to move. The Gorda plate cracks, the triple junction shifts, the offshore faults adjust. And every so often before dawn, one of those adjustments becomes large enough for the map to light up. That is what happened. A broken piece of the ocean floor moved. The coast barely felt it. The tsunami system stayed quiet. The news cycle mostly moved on. But beneath the calm surface, the same ancient machine kept running. And the next question is the one that pulls us deeper into the story. If the main Cascadia fault did not move, why does movement beside it still matter? Chapter 7. What people felt and why most felt nothing. For most people on land, the morning did not feel like history. It felt like nothing. That is one of the strangest things about offshore earthquakes. Deep beneath the Pacific, the crust can break. Millions of tons of rock can shift. Seismic waves can spread through the Earth in every direction. Instruments hundreds of miles away can record the motion clearly. And yet, in a bedroom on the coast, a person may sleep through the entire thing. That is what happened for much of southern Oregon and northern California. Some people did feel it. A few light sleepers may have woken up confused, feeling the bed move slightly, or hearing a window rattle. Someone sitting awake in the early morning may have noticed a gentle rolling sensation, the kind of motion that makes you pause and ask yourself whether it was the earth or just your imagination. In some homes, hanging objects may have swayed. In others, a loose item on a shelf may have shifted. But there was no violent jolt across the coast. No widespread panic. No buildings damaged. No emergency rooms filling with injuries. No dramatic cell phone videos from streets full of frightened people. Most of the human world stayed quiet. That does not mean the earthquake was fake, weak, or irrelevant. It means the energy had distance to travel before it reached people. The first earthquake was far offshore. By the time the strongest shaking reached land, much of the damaging high-frequency energy had already weakened. The waves that made it to the coast were softer, longer, more rolling than destructive. This is why two earthquakes with the same magnitude can feel completely different. A magnitude 5.7 directly beneath a city can damage old brick buildings, crack walls, knock things from shelves, and frighten thousands of people into the streets. A magnitude 5.7 far offshore can become only a mild rolling motion for communities on land. Same magnitude, different outcome. Location changes everything. Depth changes everything. Distance changes everything. And this is the reason public attention often fails to match scientific importance. People judge earthquakes by what they feel. Scientists judge them by what happened underground. Those are not always the same thing. For the people living near the coast, this sequence may have been forgettable. For the instruments, it was clear. For the tectonic system, it was another adjustment inside one of the most complex corners of the West Coast. That mismatch is dangerous for public understanding. Because if an earthquake causes no damage, most people assume it has no meaning. They hear no tsunami warning. They hear no injuries. They hear no damage reported, and they stop paying attention. But geology does not work according to news value. The Earth can do something meaningful without doing something visible. The coast can remain calm while the system beneath it shifts, and that is exactly what makes offshore seismic events so easy to underestimate. Imagine a huge machine behind a wall. You cannot see the gears, you cannot see the pressure building. Most of the time, the machine makes no sound at all. Then one night you hear a deep metallic knock from inside the wall. Nothing breaks, the lights stay on, the floor does not collapse. But you heard it, the machine moved. That is what this earthquake was. A knock from inside the wall, not the collapse, not the disaster. A reminder that the machine is still running. And this particular machine is old, powerful, and not fully predictable. Along the Oregon and Northern California coast, people live beside beauty that hides danger extremely well. The cliffs, the forests, the beaches, the harbors, the quiet towns. The road following the Pacific. All of it sits near a plate boundary that has spent millions of years building mountains, opening ocean basins, breaking crust, and occasionally producing earthquakes so large they alter coastlines. But most days, it looks peaceful. That peace is real, but it is not the same as safety. The coast is quiet because the system is between major ruptures, not because the system has stopped. That is why a morning like this matters even when almost nobody feels it. It shows the difference between human time and geological time. Human beings notice disaster. Geology moves continuously. Human beings notice collapsed buildings. Geology notices stress. Human beings notice headlines. Geology leaves dots on a map, and sometimes those dots are the only visible sign that something deep beneath the ocean just rearranged itself. So when people ask, if this earthquake mattered, why didn't anyone feel it? The answer is simple. Because it happened far enough offshore to protect the coast from strong shaking. That is the good news. But the reason it matters is not the shaking people felt. It is the system that produced it. That is the part people did not feel. They did not feel the Gorda plate being squeezed. They did not feel the triple junction shifting. They did not feel the long locked Cascadia interface continuing to hold stress. They felt at most a faint roll. But beneath that faint roll was a much larger story. A story of plates moving in the dark, a story of a coastline sitting beside a clock, a story that does not become less real just because most people slept through the first chapter. And that brings us to the next question. If the earthquake was offshore, moderate, and mostly unfelt, why was there no tsunami warning? Because that answer tells us something extremely important about what kind of earthquake this was, and what kind it was not. Chapter 8. Why there was no tsunami warning. After an offshore earthquake on the west coast, one question appears almost immediately. Was there a tsunami warning? For people who live along the Pacific, that question is not dramatic. It is practical. The ocean is beautiful until the wrong kind of earthquake moves the seafloor. Then the ocean becomes the danger. So when a magnitude 5.7 earthquake appeared offshore near the Oregon and Northern California coast, it was natural for people to wonder whether a wave had been generated. The answer was no. No tsunami warning. No tsunami advisory. No evacuation order. No reason for people to run from the beach or leave the harbor. And in this case, the absence of a warning was not suspicious. It was exactly what the science expected. To understand why, you have to understand what actually creates a tsunami. A tsunami is not caused simply because an earthquake happens under the ocean. That is one of the most common misunderstandings. Many underwater earthquakes do not generate meaningful tsunamis at all. To make a dangerous tsunami, an earthquake usually needs to do something very specific. It needs to move a large area of seafloor vertically, up or down, fast. When the seafloor suddenly lifts, it pushes the water above it upward. When the seafloor suddenly drops, the water above it sinks and then rushes to adjust. That displacement becomes a wave. And if the displaced area is large enough, the wave can travel across the ocean at jetliner speeds. That is what makes subduction zone earthquakes so dangerous. In a major megathrust rupture, one plate suddenly lurches over another across a huge area. The seafloor can move vertically over hundreds of kilometers. That vertical motion pushes an enormous volume of water out of place. That is how the 1700 Cascadia earthquake sent a tsunami across the Pacific to Japan. That is how the 2004 Sumatra earthquake created one of the deadliest tsunami disasters in modern history. That is how the 2011 Japan earthquake produced a wave that overwhelmed coastal defenses. But the June 3 offshore sequence was not that kind of earthquake. The reported events were moderate. They were not large enough to displace a huge area of seafloor. And more importantly, they do not appear to have been the kind of shallow thrust rupture that efficiently lifts or drops the ocean floor. This matters. An earthquake can release real energy inside the crust and still do very little to the water above it. If the fault motion is mostly horizontal, the seafloor may not rise or fall enough to generate a serious wave. If the rupture area is small, the water displacement is limited. If the event is too deep, the motion may not transfer strongly to the seafloor. That is why tsunami warning centers do not respond only to magnitude. They look at location, depth, fault mechanism, historical behavior, expected seafloor displacement, observed sea level data, and for this sequence, the ingredients for a damaging tsunami were not there. That is why no warning was issued. Not because someone missed it, not because officials were hiding something, not because the system failed. Because the earthquake did not meet the physical requirements. This is important because after any offshore earthquake, misinformation spreads fast. Someone will say they should have issued a warning. Someone else will say they cancelled the alert. Someone will claim there was a secret advisory. Someone will post a map with a red circle and imply the coast was in danger. But the ocean does not respond to red circles. It responds to physics. And the physics of this event did not support a tsunami threat. That should be reassuring. But it also teaches us the difference between this event and the one Cascadia is famous for. The Cascadia megathrust is dangerous specifically because it can move the seafloor vertically over a very large region. When the locked interface finally breaks in a major rupture, parts of the coast may drop. Offshore areas may rise, the water above them will be displaced, and the tsunami risk will be immediate. That is the nightmare scenario. This was not that. This was movement in the surrounding offshore system. Important. Interesting, worth watching, but not the kind of rupture that produces a major tsunami. This distinction is everything. A moderate internal plate earthquake offshore is one kind of event. A full Cascadia megathrust rupture is another. They may occur in the same broad tectonic neighborhood, but they are not mechanically identical. One can rattle the coast lightly and produce no wave. The other can reshape the shoreline and send water across the Pacific. That is why the lack of tsunami warning is actually one of the strongest clues about what this earthquake was not. It was not a large, shallow thrust rupture on the main Cascadia interface. It was not the kind of vertical seafloor displacement event that emergency managers fear most. It was not the big one. But again, that does not make it meaningless. Because the earthquake happened near the system capable of producing that larger event. Think of it like hearing a small sound near a locked vault. The sound does not mean the vault opened, but it reminds you where the vault is. The ocean stayed calm this time. No major wave formed. No warning was needed. The warning system did what it was supposed to do by not alarming people unnecessarily. That is good. But someday, when Cascadia itself ruptures in the wrong way, the situation will be very different. There may be only minutes for some coastal areas, not hours. Minutes. That is why tsunami evacuation routes exist. That is why signs point uphill in coastal towns. That is why people along the Pacific Northwest are told that if they feel strong shaking near the coast, they should not wait for an official alert. They should move to high ground, because in a true nearby Cascadia tsunami scenario, the ground shaking itself may be the first warning. This morning did not bring that. This morning brought a moderate offshore sequence with no significant tsunami threat. The ocean did not rise. The coast did not evacuate. The warning centers stayed quiet because the data supported quiet. But the absence of a tsunami does not end the story. It only sharpens the next question. If the earthquake did not happen on the main tsunami-generating Cascadia fault, then what fault did move? And why does movement beside Cascadia still matter? Chapter 9. The Fault. Everyone is watching was not the one that moved. The most important thing to understand about this earthquake sequence is also the easiest thing to misunderstand. It happened near Cascadia, but that does not mean it happened on Cascadia. Those two sentences are not the same. And the difference between them is the difference between a notable offshore earthquake and a true regional emergency. The Cascadia subduction zone is the Great Locked Fault beneath the Pacific Northwest. It is the interface where oceanic crust is being forced beneath North America. It is the fault that last produced a catastrophic full margin rupture in January of 1700. It is the fault capable of generating a magnitude 9 earthquake. It is the fault that emergency planners in Oregon, Washington, Northern California, and British Columbia study with extreme seriousness. That is the fault everyone watches. But the earthquakes in this sequence do not appear to have occurred directly on that main locked megathrust interface. They happened nearby within the surrounding plate boundary system, most likely associated with internal deformation inside the Gorda plate and related offshore structures. That is a very different kind of event. A megathrust earthquake happens along the broad contact between the subducting oceanic plate and the overriding continental plate. That fault is shallowly dipping. It is huge. It can rupture over hundreds of kilometers. It can move the seafloor vertically. It can generate severe shaking and a tsunami. An internal Gorda plate earthquake is different. It happens inside the oceanic plate itself. It may occur on a steep internal fault. It may involve more horizontal motion. It is usually much smaller in rupture area. It does not simply unzip the Cascadia interface. That distinction is good news. Very good news. Because if the main Cascadia interface had ruptured significantly, the story would be completely different. There would likely have been stronger shaking. There may have been a tsunami evaluation. The event would have drawn much more attention from emergency systems. Scientists would be analyzing whether the locked zone had begun to fail. But that is not what the public data suggested. Instead, the event appears to belong to the restless surrounding system. The broken plate beside the locked fault. The cracked neighborhood around the dangerous door. This is where the science becomes subtle. Because saying the main Cascadia fault did not move is not the same as saying the event has no relationship to Cascadia. The Earth is not divided into isolated boxes. Faults exist inside stress fields. Plates push on one another. A rupture in one place changes the stress nearby. The changes are usually small, but they are real. When a fault slips, it does not only release energy from its own rupture surface. It also rearranges the forces in the surrounding crust. Some nearby regions may become slightly less stressed. Others may become slightly more stressed. This is not mystical. It is mechanical. It is the same basic idea as pressing on one part of a cracked windshield and seeing the stress change elsewhere in the glass. Most of the time, nothing dramatic follows. The crack does not spread. The system adjusts. The sequence fades. That is the most likely outcome here. But the reason scientists still pay attention is that the main Cascadia fault is already loaded over long time scales. It has been accumulating strain for centuries, so even small changes near the southern end of the system are worth watching, not because they predict a rupture, but because they happen in a region where the long-term hazard is real. This is the difficult middle ground. The earthquake did not break the fault everyone fears, but it happened close enough to that fault to remind us why the region is watched. And it happened in a place where different fault systems are close together. The Gorda plate, the Cascadia interface, the Mendocino fracture zone, the northern reach of the San Andreas system, the triple junction. This is not a clean map. It is a crowded mechanical system. And when one part shifts, scientists ask what changed around it. Not because they expect catastrophe every time, but because sometimes earthquakes interact. The 1992 Cape Mendocino sequence showed that clearly. A major event on one structure was followed by significant earthquakes on adjacent structures. That does not mean every sequence becomes a cascade. Most do not. But it proves that this region can transfer stress across boundaries. That is why the phrase "not on Cascadia" should reassure you, but not put you to sleep. It means this was not the big one. It means the main locked fault did not appear to fail in this sequence. It means no immediate tsunami-generating rupture occurred. But it does not erase the larger context. The dangerous fault is still locked. The surrounding plates are still moving. The southern end of the system is still complex. The clock is still running. This is why the correct interpretation must hold two ideas at once. First, this earthquake sequence is most likely routine activity in a highly active offshore region. Second, routine activity near a loaded megathrust is still worth understanding. The public often wants one of two answers. Either, there is nothing to see here, or this is the warning. But the Earth rarely gives us answers that clean. The more honest answer is, this was not the fault everyone fears. But it happened beside it. And movement beside a locked fault is not the same as movement nowhere. That is the tension at the center of this story. The main Cascadia interface stayed quiet. The Gorda Plate did not. The coast was safe. The system was active. No disaster happened. But the map lit up in the neighborhood where one eventually will. And to understand why that matters, we have to talk about one of the most important ideas in modern earthquake science: stress transfer. The small push that means nothing unless the fault next door is already close to breaking. Chapter 10. Stress transfer, the small push that matters only if a fault is ready. Earthquakes are not isolated events. They feel isolated to us because we experience them as moments. A sudden jolt, a few seconds of shaking, a dot on a map, a number in a report. But underground, every earthquake is part of a stress system. The crust is already under pressure before the rupture begins. The fault is already loaded. The rock is already strained. Then one section slips. And when it slips, the stress does not vanish. It moves. Some of it is released. Some of it is redistributed. Some nearby faults are relaxed. Others are nudged closer to failure. This is called stress transfer, and it is one of the reasons scientists pay attention to earthquake clusters. The idea is simple, but the implications are complicated. Imagine a table covered with cracked glass. The glass has many fractures running through it. Some cracks are old, some are fresh, some are barely visible. Now press down on one part. A crack may shift. When it does, the pressure pattern in the glass changes. One nearby crack may become less likely to spread. Another may become more likely. The movement of one crack does not guarantee the movement of another. But it changes the conditions. The Earth behaves in a similar way. When a fault ruptures, it changes the stress in the surrounding crust. Not everywhere equally, not always in the same direction, and usually not by a huge amount. But the change can be measured, modeled, and sometimes linked to later earthquakes. This is why the June 3 sequence matters scientifically. A moderate earthquake inside or near the Gorda Plate does not automatically threaten Cascadia. It does not mechanically turn into a magnitude 9 rupture. It does not unzip the megathrust, but it can slightly change the stress field nearby. And nearby includes parts of the southern Cascadia system. How much does it change the stress? Usually not much. For an event of this size, the stress changes at distances of tens of kilometers may be small, often too small to have any obvious effect. By the time you move farther away, the effect becomes even weaker. That is why most moderate earthquakes do not trigger major events. If every magnitude 5 or 6 quake near a major fault caused the big one, the world would look very different. But the important phrase is this: usually too small. Not always meaningless. A small push can matter if the system receiving the push is already very close to failure. Think about a rock balanced on the edge of a cliff. If it is sitting firmly, a breeze does nothing. If it is already tipping, a breeze can finish the job. The breeze did not create the instability. It only decided the timing. That is how stress transfer can work. It does not create centuries of tectonic strain in a moment. The strain is already there. Plate motion built it. Time stored it. Fault friction held it. Then a nearby earthquake can slightly shift the balance. Most of the time, the effect is too weak to matter. Sometimes it is enough to change when a nearby fault fails. This is why scientists cannot simply say, nothing changed. Something did change. The question is whether the change matters. And that is much harder to answer. For the southern Cascadia region, the difficulty is even greater because the geometry is complex. The main interface dips beneath the continent. The Gorda Plate is internally fractured. The Mendocino triple junction involves multiple plate boundaries. The faults are not arranged like clean lines on a flat page. They are three-dimensional surfaces interacting beneath the ocean and the continent. To calculate stress transfer accurately, scientists need to know the exact fault that slipped, the direction of motion, the depth, the rupture area, and the geometry of nearby faults. In the first hours after an offshore earthquake, some of that information is uncertain. That means the most careful answer is not dramatic. It is conditional. If the rupture happened on this fault, stress may have increased here. If it happened on that fault, stress may have decreased there. If the depth is revised, the pattern changes. If the mechanism is different, the stress map changes. This is not weakness in the science. It is honesty about the system. The Earth is complicated. The first data is incomplete. And good science does not pretend precision before it has it. So what should we say about stress transfer from this sequence? The honest version is this. The earthquakes likely change the stress field in the surrounding offshore region by a small amount. Most likely that change will not produce anything larger. Most likely the system will settle back toward background activity. But because the events happened near the southern Cascadia system, scientists will still watch the catalogue, the tremor data, and the GPS signals for anything unusual. That is the calibrated position. Not panic, not dismissal. Attention. This is the word that keeps coming back. Attention. Because stress transfer is not prediction. It does not tell us that a larger earthquake is coming. It does not give a countdown. It does not say tomorrow, next week, next year. It only says that after one fault moves, the surrounding system is not exactly the same as it was before. And in a place like the Mendocino Triple Junction, that matters. The Triple Junction is already active. The Gorda Plate is already cracked. The Cascadia interface is already locked. The San Andreas system is nearby. This is a region where faults do not exist in isolation. They share stress. They respond to regional motion. They sometimes trigger activity across boundaries. That does not happen every time, but it has happened before. And to understand that, we need to go back to one of the most important earthquake sequences in Northern California history. The year was 1992. The place was Cape Mendocino, and that time the corner did not just whisper, it struck hard. Chapter 11, 1992. The warning from Cape Mendocino. If you want to understand why scientists respect the Mendocino Triple Junction, you have to understand what happened in April of 1992, because that sequence showed what this corner of the Earth can do when it truly wakes up. On April 25, 1992, a powerful earthquake struck near Cape Mendocino. It was not a small offshore pulse. It was a major event. Magnitude 7.2, strong enough to damage buildings, strong enough to injure people, strong enough to remind Northern California that the southern end of Cascadia is not just a line in a scientific paper. It is a living fault system capable of violence. The shaking was intense near the epicentral region. Communities in Humboldt County felt it sharply. Structures were damaged. Fires broke out. People were injured. For those who lived through it, this was not an abstract geological event. It was dishes falling, walls cracking, roads shaking, and the sudden realization that the ground beneath the coast could become unstable without warning. But the main shock was only the beginning. In the hours that followed, the system kept moving. Large offshore earthquakes struck after the first major event. These were not identical copies of the main shock. They occurred on adjacent structures, different faults, different mechanisms, different pieces of the same tectonic corner responding to the stress change. That is why 1992 is so important. It showed that at Cape Mendocino, earthquakes can interact across structures. A rupture in one part of the system can alter the stress in another. The region can produce a sequence, not just a single isolated event. This does not mean every earthquake there becomes a cascade. Most do not. But 1992 proved that cascades are possible. And it proved something else equally important. A cascade can stop. The 1992 sequence did not become a full Cascadia rupture. It did not unzip the entire megathrust from Northern California to Vancouver Island. It did not trigger the San Andreas into a massive rupture. It did not become the worst-case scenario. It was powerful. It was damaging. It was scientifically important. But it stayed limited. That is why the 1992 sequence is such a useful comparison. It teaches caution in both directions. It warns against dismissal because the region clearly can produce multi-event sequences. But it also warns against panic because even a much larger sequence than the June 3 events did not automatically grow into the big one. This is the balance we need. The Earth has shown us that this corner can transfer stress. It has also shown us that stress transfer does not mean runaway disaster. The difference between 1992 and the recent offshore sequence is also important. In 1992, the largest event was a major magnitude 7 class earthquake. It caused real damage and clear, strong shaking. The follow-on events were significant. The sequence was obvious. The June 3 sequence was much smaller. The largest event was around magnitude 5.7. The following events were smaller. The shaking on land was light. No damage was reported. No tsunami warning was needed. So if we are comparing the two, we should not exaggerate. June 3 was not 1992, but it happened in the same broad tectonic world. The same corner. The same neighborhood of interacting plates. The same region where the Gorda Plate, Cascadia, and the Pacific Plate system meet in a complicated geometry. That is why 1992 sits in the background of every serious conversation about earthquakes near Cape Mendocino. It is the reminder that the corner is capable of more. Not always, not usually, but sometimes. And when it does more, the sequence can move from one structure to another. That is the lesson. The June 3 sequence, at least in its early public pattern, did not look like a major escalating cascade. The largest event came first. Later events were smaller. That is more consistent with a main shock aftershock style pattern than a clear build-up. That is reassuring, but it does not erase the historical lesson, because the region has a memory, not memory in a mystical sense, memory in a geological sense. The faults are still there. The stress field is still there. The plate motions that produced the 1992 sequence are still operating. The Gorda plate is still being crushed. The Cascadia interface is still locked. The triple junction is still one of the most active corners of the west coast. And every time the map lights up there, 1992 becomes relevant again. Not because the same thing is happening, but because it shows what can happen. For viewers, the most important takeaway is this. The recent sequence does not mean a major rupture is imminent. But history shows that this region can produce larger sequences when conditions are right. The problem is that we rarely know in advance when conditions are right. That is why scientists watch. That is why emergency planners prepare. That is why we study old events. Because the Earth gives examples before it gives warnings. 1992 was one of those examples. A hard strike from a dangerous corner. A proof that the southern end of the Cascadia system is not passive. A reminder that the boundary can move violently without involving the entire margin. And a warning that the next major event in this region may not begin with a clean, obvious signal. It may begin with a sequence, a cluster, a shift, a dot on a map. Or it may arrive with no useful warning at all. To understand why that uncertainty matters so much, we have to go further back. Not to 1992, not to modern instruments, but to a winter night more than 3 centuries ago, when Cascadia did not whisper. It broke. Chapter 12. The 2024 Reminder. When the warning system blinked. Before we go all the way back to 1700, there is a more recent reminder worth understanding. Because the West Coast did not need to wait centuries to see this region produce a stronger offshore event. In December 2024, the Cape Mendocino region reminded everyone again why it is watched so carefully. A strong offshore earthquake struck near Northern California. It was large enough to be felt widely, large enough to trigger serious attention from emergency systems, large enough that a tsunami warning was issued out of caution before later being cancelled when observations showed that a significant tsunami had not formed. That event matters in this story because it shows how the warning system behaves when the size, location, and mechanism of an offshore earthquake raise concern. When a stronger event happens near the coast, warning centers do not wait for perfect information. They begin with rapid estimates. They ask the most important immediate question. Could this earthquake have displaced enough seafloor to create a tsunami? If the answer is possibly yes, they warn first and refine later. That is not failure. That is how a cautious system is supposed to work. A warning can be cancelled. Lives cannot be replaced. So when the 2024 event triggered a warning, the system leaned toward caution. Then, as tide gauges and sea level observations came in, the threat was reassessed. The warning was lifted. Some people looked at that and thought the system overreacted. But that is the wrong lesson. The right lesson is that the system functioned in the way it was designed to function. It recognized uncertainty. It acted early. Then it corrected based on better data. That is exactly what you want from a tsunami warning system. Now compare that with the June 3 sequence. This time no warning was issued. Why? Because the events did not meet the same threat profile. They were smaller. They were not clearly the kind of large, shallow thrust rupture that creates major vertical seafloor displacement. They did not require a precautionary coastal warning, so the system stayed quiet. And that quiet response is just as meaningful as the warning response in 2024. In 2024, the system blinked because the event was big enough and uncertain enough to justify caution. In June 2026, the system did not blink because the physics did not support a tsunami threat. Both responses can be correct. This is important because people often judge warnings emotionally. If a warning is issued and nothing happens, they call it fear-mongering. If no warning is issued, they call it suspicious. But emergency science is not about emotional satisfaction. It is about thresholds, probability, worst-case modeling, observed data, and time, especially time. After an offshore earthquake, time is the enemy. If a dangerous local tsunami has been generated, coastal communities may have minutes. There is no luxury of waiting for a perfect academic analysis. That means early warnings must sometimes be issued under uncertainty. But it also means warnings should not be issued when the event clearly does not meet the physical criteria. Otherwise, people stop trusting the system. The 2024 event and the June 3 sequence show both sides of that balance. Warn when the possible threat is real. Do not warn when the event type does not justify it. That is how public trust is built. The 2024 event also shows something else. Even a strong offshore earthquake in this region does not automatically mean a catastrophic tsunami. The details matter. Fault motion matters. Seafloor displacement matters. Actual ocean observations matter. And this is why every earthquake in the Cape Mendocino region must be judged on its own mechanics, not just its location. Location raises attention. Mechanism defines threat. Magnitude shapes urgency. Observation confirms reality. This is the chain. The June 3 sequence sits lower on that chain. It was meaningful enough to study, not strong enough to trigger a tsunami response. That should calm people, not confuse them. But it should not make them forget the larger hazard. Because the warning system is not the same as prediction. A tsunami warning system can respond after an earthquake begins. It cannot tell you days ahead of time that Cascadia is about to rupture. The same is true for earthquake early warning. Systems like Shake Alert can detect the first waves from an earthquake and send alerts before stronger shaking arrives in some areas. That can provide seconds, maybe tens of seconds, enough to drop, cover, and hold on, enough to slow trains, enough to open fire station doors, enough to stop elevators. But it is not prediction. It is detection after the rupture has already started. That is why events like June 3 matter. They sit in the uncomfortable space before detection, before disaster, before certainty. They are not warnings from the official system. They are not predictions. They are reminders. The 2024 event reminded the coast that a stronger offshore earthquake can trigger emergency systems quickly. The June 3 event reminded the coast that smaller offshore sequences can happen quietly and pass without public attention. Both are part of the same reality. This region moves. Sometimes it moves enough to make the warning system blink. Sometimes it moves in the dark and almost nobody notices. But the larger machine beneath the coast is always there. And that machine has produced something far larger than either 2024 or June 2026. To understand that, we have to go back to the night Cascadia proved what it could do. A night before seismometers, before tsunami sirens, before highways, ports, power lines, cell towers, and modern cities. A night when the coast itself dropped, and a wave crossed the Pacific with no known parent. Chapter 13. January 26, 1700, the night Cascadia proved it was real. The most important earthquake in Pacific Northwest history happened before anyone had a seismometer there to record it. There was no Richter scale, no USGS feed, no tsunami warning center, no phones, no sirens, no emergency broadcast. And yet we know the date, January 26, 1700. We know it not because a machine recorded the shaking, but because the earthquake left evidence in 3 different worlds. In the forests of the Pacific Northwest, in the oral histories of indigenous peoples along the coast, and across the Pacific Ocean in the written records of Japan. That is what makes the 1700 Cascadia earthquake so haunting. It was invisible to modern instruments, but it was not hidden from history. That night, the Cascadia subduction zone ruptured on an enormous scale. The locked boundary between the oceanic plate and North America gave way. The coastline shook violently. Parts of the coast dropped suddenly. Forests that had stood on dry ground sank low enough for saltwater to reach their roots. Trees died where they stood. Over time, mud and tidal sediment buried their bases. Centuries later, scientists would find those dead forests and call them ghost forests. They were not legends, they were evidence. Stands of trees killed at the same time. Their final growth rings pointing to the same period. Their roots still planted in soil that had once been above the tide. The land had dropped. Not slowly. Not over generations, in minutes. That is what a major subduction earthquake can do. It does not just shake buildings, it changes the elevation of the coast. It redraws the relationship between land and sea. But the ghost forests were only one part of the puzzle. Indigenous oral histories from coastal peoples preserved memories of a night of violent shaking and destructive water, stories told of villages hit by waves, canoes carried inland, people fleeing to higher ground, communities changed by a sudden disaster from the sea. For a long time, Western science did not treat oral histories with the seriousness they deserved. But as geological evidence accumulated, it became clear that these stories were not vague myths. They were cultural memory of a real event, a massive earthquake, a tsunami, a coastal catastrophe preserved through generations. And then there was Japan. On the morning of January 27, 1700, Japanese coastal communities recorded a tsunami, but there had been no felt earthquake in Japan, no local shaking, no obvious source. The wave arrived from across the Pacific like an orphan. Historical records described flooding and damage along parts of the Japanese coast. For centuries, the source remained unknown. Then scientists connected the timing. A tsunami generated in Cascadia on the evening of January 26, local time, would cross the Pacific and arrive in Japan on January 27. The ghost forests, the indigenous histories, and the Japanese records all pointed to the same event, a massive Cascadia rupture. Likely magnitude 8.7 to 9 or greater, a rupture capable of sending energy across an ocean. That is how we know Cascadia is not theoretical. The danger is not based on imagination. It already happened. The modern Pacific Northwest is built beside a fault with a proven history of catastrophic rupture. The only reason many people underestimate it is that the last full margin event happened before the modern region existed, before Seattle became a major city, before Portland grew into a major metro area, before highways connected the coast, before bridges, pipelines, electrical grids, ports, hospitals, data centers, airports, and modern supply chains filled the region. The last Cascadia rupture happened to a coastline that was inhabited, remembered, and deeply affected. But it did not happen to the modern built environment. That is the key. The next one will. Whenever it comes, it will not be an abstract geological event. It will be a modern infrastructure test. And that is why the 326-year clock matters. Because since that night in 1700, the Cascadia interface has been loading again. The plates did not stop moving after the rupture. They resumed their slow motion. The oceanic plate continued pressing beneath North America. The locked areas began storing energy again. The coast continued its long, quiet wait, year after year, decade after decade, century after century. Most people living in the region will never feel the slow loading. They will only experience the release if it happens in their lifetime. That is what makes subduction zones so deceptive. They do not need to remind people every decade with catastrophic earthquakes. They can remain quiet long enough for societies to become comfortable, long enough for cities to expand, long enough for memories to fade, long enough for people to treat the absence of recent disaster as proof of safety. But geological silence is not safety. Sometimes silence is storage. That is Cascadia. The quiet is not empty. It is loaded. This is why a moderate offshore sequence in 2026 immediately pulls the mind back to 1700. Not because the two events are the same. They are not. Not because the recent sequence means a repeat is imminent. The data does not show that, but because both belong to the same long system, the same margin, the same subduction cycle, the same coastline living between major releases. The 1700 event is the shadow behind every Cascadia discussion. It is the reason emergency planners care. It is the reason tsunami evacuation routes exist. It is the reason scientists study offshore sediment cores, coastal marshes, GPS stations, tremor bursts, and earthquake clusters. Because the system has already shown its maximum form, and the modern world has not yet faced it. That is what makes the story so unsettling. The June 3 sequence was small. The 1700 rupture was enormous. Between those two facts lies the whole problem. The Earth gives small movements all the time. Most mean nothing beyond themselves. But one day the movement will not stay small. One day the locked boundary will break again. And when it does, the evidence will not be hidden in ghost forests for future scientists to discover. It will be recorded live, by phones, by satellites, by seismic networks, by warning systems, by people running uphill, by cameras pointed at bridges, ports, and coastlines. The 1700 earthquake proved what Cascadia can do. The next one will prove what the modern Pacific Northwest can survive. And that is why the clock matters. Chapter 14. The 326-year clock. As of June 2026, more than 326 years have passed since the last great Cascadia rupture. That number sounds precise, 326 years, but it is important not to misunderstand what it means. Earthquake faults do not follow human calendars. They do not have appointments. They do not become due in the way rent becomes due or a train becomes late. A recurrence interval is not a schedule. It is an average built from the past. And the past is irregular. Sometimes a fault ruptures after a shorter wait. Sometimes after a longer one. Sometimes the whole margin breaks. Sometimes only a segment breaks. Sometimes the southern portion behaves differently from the northern portion. So when people say Cascadia is overdue, the phrase can mislead. A better way to say it is this. Cascadia is loaded. The clock is real. But the clock has no visible hands. We know the system has ruptured before. We know it will rupture again. We know strain is accumulating. We know the plates keep moving. We know the locked interface cannot hold forever. What we do not know is when the next major release will occur. That is the heart of the problem. The 326-year quiet period is not proof that the next earthquake is imminent, but it is long enough to matter, especially near the southern segment. The Cascadia system is not one perfectly uniform fault. Different parts of the margin may rupture in different ways. A full margin rupture, like the 1700 event, is the largest scenario. That kind of event may have an average recurrence time of several centuries. But partial ruptures, especially involving the southern portion, may happen more often. That distinction matters because the June 3 sequence happened near the southern end of the system, near the Gorda Plate, near the Mendocino Triple Junction, near the place where Cascadia transitions into a much more complicated plate boundary. If you are thinking only about a full margin magnitude 9 rupture, 326 years is significant but not extreme compared with the long historical range. If you are thinking about a southern segment event, the same 326 years becomes more interesting. Not alarming by itself, but more interesting. That is why the clock should not be used to create panic, but it also should not be ignored. A loaded fault does not need to be overdue to be dangerous. It only needs to be capable. Cascadia is capable. The geological record proves it. The paleoseismic record shows repeated large earthquakes over thousands of years. Offshore sediment layers, coastal subsidence records, tsunami deposits, and the 1,700 historical evidence all point to a system that fails again and again over geologic time. Human civilization along the Pacific Northwest coast exists in the quiet space between those failures. That is not meant to be dramatic. It is simply true. We build during quiet intervals. We expand during quiet intervals. We forget during quiet intervals. Then the fault reminds us, sometimes with a small offshore sequence, sometimes with a larger regional earthquake, eventually with a major rupture. The challenge is that small reminders do not tell us exactly where we are on the clock. They do not tell us whether the next great earthquake is near. They do not reset the system in any obvious way. They do not give certainty. They give context. The June 3 earthquake sequence belongs in that context. By itself, it does not change the long-term probability dramatically. It does not mean the next Cascadia event is coming this week. It does not mean people should leave the coast. It does not mean the government is hiding an imminent disaster, but it happened inside the broader system that is accumulating stress. And it happened after 326 years of quiet on the largest scale. So it becomes a reminder of the clock, a clock that cannot be read precisely, a clock that does not tick evenly, a clock that may run for another century or more, or may stop on an ordinary morning. That uncertainty is difficult for people to live with. Human beings like clear answers, safe or unsafe, now or never, warning or nothing. But earthquake science does not offer that kind of comfort. The most honest answer is often the least satisfying one. The probability of a major Cascadia rupture in any given week is very low, but the probability over decades is meaningful. That is why preparedness is rational even when panic is not. If you live near the coast, you do not prepare because this one sequence guarantees disaster. You prepare because the long-term hazard exists with or without this sequence. You prepare because Cascadia has ruptured before. You prepare because it will rupture again. You prepare because when it happens, the warning may be short. And you prepare because preparation is one of the few parts of this story human beings can control. The plates will move. The Gorda Plate will continue cracking. The Cascadia interface will continue loading. The triple junction will continue producing earthquakes. None of us can stop that. But people can know evacuation routes. They can store water. They can secure heavy furniture. They can make family communication plans. They can learn what strong coastal shaking means. They can understand that if they are near the beach and the ground shakes hard or long, they should move uphill without waiting for a message. That is not fear. That is literacy, geological literacy. And that is what the 326-year clock should create. Not panic, literacy. The clock is not there to terrify people. It is there to remind people that the quiet coast is part of a cycle. A beautiful coast, a living coast, a dangerous coast, a coast shaped by forces much larger than us. The June 3 sequence did not start the big one, but it happened under the shadow of the last one. And it happened while the clock continues to run toward the next. That is why this story matters. Not because today is the day, but because one day will be. And when that day comes, it will probably begin like any other day. Dark ocean, sleeping towns, quiet roads, a few instruments waiting in silence. Then the first wave through the rock, the first dot on a screen, the first sign that the clock has finally struck. Until then, all we have is the long quiet, the small reminders, and the responsibility to pay attention without losing our heads. The clock is running. It has been running for 326 years, and whether this morning meant anything more than routine movement or not, the larger truth remains unchanged. Cascadia is still locked. The plates are still moving, and the next chapter is still somewhere ahead. Chapter 15. what a real foreshock pattern might look like. This is the part of the story where we have to be very careful, because after an earthquake cluster happens near a major fault, one word appears almost immediately: foreshock. People ask it in comments. They ask it on social media. They ask it in local Facebook groups. They ask it quietly in their own homes if they live near the coast. Was this a foreshock? And the most honest answer is uncomfortable. Maybe, but probably not. That answer sounds weak, but it is actually the strongest answer the science can give. Because a foreshock is not something scientists can always identify in real time. A foreshock gets its name only if a larger earthquake happens afterward. Before the larger earthquake, it is just an earthquake. That is the problem. The same event can be routine on Monday and become a foreshock on Friday if a larger rupture follows. Nothing about the original earthquake changes. Only the future changes its meaning. That is why earthquake forecasting is so difficult. We can look for patterns. We can compare sequences. We can measure rates. We can watch tremor. We can track GPS motion. But we cannot yet look at a single moderate earthquake and confidently say, this is the warning. The Earth does not label its warnings for us. Still, scientists do know some of the patterns that sometimes appear before larger earthquakes. The first is acceleration. Before some major earthquakes, the rate of smaller events increases. Not just one quake, not just one aftershock. A growing rhythm, more events over time, shorter gaps between them, a region that begins to light up faster and faster. If you imagine a kettle coming to boil, that is the idea. At first, only a few bubbles rise, then more. Then the whole surface begins to move. Some foreshock sequences behave like that. The seismicity rate increases before the main rupture. But the June 3 sequence, at least in its early public pattern, did not clearly show that. The largest event came first. The later events were smaller. The sequence did not immediately build upward in magnitude. That is more consistent with a main shock aftershock pattern than a classic foreshock build-up. The second possible sign is increasing magnitude. In some foreshock sequences, the events do not just become more frequent, they become stronger. A magnitude 3, then a 4, then a 5, then a larger rupture. That kind of pattern gets attention because it suggests the system may be progressively destabilizing. But again, that was not the obvious pattern here. The first quake was the largest. After that, the sequence stepped down. That does not guarantee safety, but it leans toward routine. The third possible sign is spatial migration. That means earthquakes begin moving in a pattern across the map. They may creep toward a future rupture zone. They may line up along a fault. They may appear to move north, south, up dip, down dip, or toward a known locked patch. This can be important because a migrating sequence may show stress spreading through a system. But the offshore sequence did not clearly show one clean migration path. It looked more like a cluster in a highly active tectonic corner than a fault preparing to unzip in one direction. Again, that is reassuring, but not final. The fourth possible sign is depth change. Sometimes, before larger events, smaller earthquakes may begin occurring at changing depths. They may become shallower. They may cluster near a particular boundary. They may reveal movement toward the main locked interface. But offshore depth estimates are tricky in the first hours after an event. Because most instruments are on land, early depth solutions can shift after review. So depth patterns must be treated carefully. A strange early depth does not prove anything mysterious. It may only prove that the automated system had limited geometry. The fifth possible sign is slow slip. This one is especially important for subduction zones like Cascadia. Not all plate movement happens as a sharp earthquake. Sometimes the fault moves slowly. Too slowly for people to feel, too slowly to produce damaging shaking, but fast enough for sensitive GPS stations to detect. This is called slow slip. In Cascadia, slow slip and tremor events happen periodically on deeper parts of the subduction system. They are part of the normal behavior of the margin. But scientists watch them because slow slip can change stress on nearby locked areas. A slow slip event is not automatically dangerous. Most happen without triggering a major earthquake. But if a moderate earthquake cluster occurs near a region of active tremor or slow slip, scientists pay closer attention, not because it means catastrophe, because it means multiple parts of the system are moving or adjusting at the same time. That is the careful scientific mindset. One earthquake is data. A cluster is more data. A cluster plus tremor changes is even more data. A cluster plus tremor changes plus GPS motion plus migration plus increasing magnitude would be much more concerning. But one moderate sequence alone does not carry that level of evidence. That is why the correct question is not simply, was this a foreshock? The better question is, does this sequence show the features that would make a foreshock interpretation stronger? So far, the answer appears to be no. Not clearly. Not based on the early public pattern. The sequence does not scream escalation. It does not clearly migrate. It does not show a steady increase in magnitude. It does not look like a textbook warning. But here is the uncomfortable part. Many real foreshocks do not look like textbook warnings either. That is the trap. If all foreshocks were obvious, earthquake prediction would be much easier. But the historical record shows that many events only become meaningful in hindsight. A moderate earthquake happens. People study it. It seems routine. Then, days later, a larger earthquake strikes. Suddenly, the earlier event is renamed. It becomes a foreshock. The original data did not announce itself. It only became part of the story after the main shock. That is why scientists do not dismiss foreshock questions completely. They keep probabilities low, but not zero. They watch. They update. They compare. They wait for the sequence either to decay or evolve. This is the hardest thing for the public to accept. The absence of a clear warning signal is not proof that nothing will happen. It is only evidence that no clear warning signal is visible. Those are different statements. For the June 3 sequence, the most likely outcome is still quiet decay. The cluster fades. The catalogue is refined. The coast moves on. But if another larger event were to follow, the June 3 sequence would instantly be reinterpreted. That is the uncomfortable truth. It is probably routine, but it cannot be declared meaningless with absolute certainty in real time. That is why this story deserves calm attention. Not fear. Not hype. Attention. Because the future is what decides whether a moderate earthquake was just a moderate earthquake. And until that future arrives, the best we can do is read the pattern honestly. So far, the pattern does not look like a clear foreshock. That matters. But it does not close the case. Chapter 16, why this does not look like a clear foreshock. Now let's put the evidence on the table plainly. If you are watching this because you are worried that the June 3 offshore sequence might be the start of something much larger, this chapter is important. Because the early pattern gives several reasons not to panic. The first reason is simple. The largest event came first. In many ordinary earthquake sequences, one main shock occurs and then smaller aftershocks follow. That is the most common pattern. The fault releases stress. The surrounding crust adjusts. Smaller events occur nearby. Then the rate declines. That appears closer to what happened here than a classic foreshock escalation. The first offshore event was the strongest. The later events were smaller. That does not prove nothing else can happen, but it is not the pattern you would expect from a clean build-up toward a larger rupture. The second reason is that there was no immediate rapid climb in magnitude. If the system were clearly accelerating toward a larger event, scientists would pay close attention to whether the maximum magnitude was increasing. But the early sequence did not step upward. It stepped downward. That is reassuring. The third reason is that there was no obvious explosive increase in event rates. Yes, several earthquakes occurred in a short time window. That matters. But earthquake clusters are common near the Mendocino Triple Junction and inside the Gorda Plate system. This is an active region. A cluster there does not automatically mean something extraordinary is beginning. The fourth reason is that the events did not clearly occur on the main Cascadia megathrust. This is extremely important. The fault capable of producing a magnitude 9 Cascadia rupture does not appear to be the structure that broke in the sequence. Instead, the events appear more consistent with activity in the surrounding offshore system. That does not make them irrelevant, but it makes them very different from the beginning of a full-margin megathrust rupture. The fifth reason is that there was no tsunami warning. This tells us the event was not the kind of large, shallow, vertical displacement earthquake that immediately threatens the coast with a wave. Again, this was not the big one. It did not behave like the big one. It did not produce the consequences of the big one. The sixth reason is historical. The Mendocino Triple Junction produces frequent moderate earthquakes. Magnitude 4 seconds and 5 seconds are not rare in this region. Even magnitude 6 range activity can occur without leading to a major Cascadia rupture. The region is restless by nature. That means not every restless moment is a warning. Most are not. Most are simply the system doing what it does. This is the side of the argument that people need to hear clearly, because fear spreads faster than nuance. A map with several earthquake dots near Cascadia can look terrifying if you do not know the baseline. But baseline matters. If a quiet region suddenly produces a cluster, that means one thing. If a chronically active tectonic corner produces a cluster, that means something else. The Mendocino region is not quiet. The Gorda Plate is not calm. This is not a dead zone suddenly waking up. It is an active zone producing activity. That is a major difference. So if we are being scientifically honest, the early evidence leans strongly toward routine seismicity. Maybe elevated routine seismicity, maybe an interesting pulse, but still within the range of what this region can do without leading to disaster. That should calm the most extreme interpretations. This does not look like a clear foreshock sequence. It does not look like Cascadia beginning to rupture. It does not justify dramatic claims that the West Coast has hours or days left before catastrophe. Anyone making that claim is going beyond the data. But there is another mistake on the opposite side. And that mistake is saying, because it does not look like a clear foreshock, it definitely is not one. That is also too confident. The Earth has surprised scientists before. Foreshock sequences can be messy. Some major earthquakes have had obvious precursors. Others have had none. Some foreshocks looked ordinary until the larger event happened. This is why earthquake science lives in probability, not certainty. The most likely interpretation is routine. The less likely interpretation is precursor. The impossible interpretation is certainty. Nobody can honestly tell you this sequence guarantees a larger earthquake. Nobody can honestly tell you it absolutely cannot be related to one. The data simply does not support either extreme. So what do we do with that? We stay calibrated. We do not panic. We do not dismiss. We watch for changes. If the event rate drops, that supports the routine interpretation. If magnitudes stay small, that supports routine decay. If the earthquakes scatter without migration, that supports routine activity. If no GPS anomaly appears, if tremor remains normal, if no larger adjacent event follows, then the sequence becomes another entry in the long history of offshore Mendocino activity. But if the pattern changes, the interpretation changes. That is how science works. It updates. It does not lock itself into a conclusion for emotional comfort. This is the key message of the whole video. The June 3 sequence does not look like a warning, but it happened in a place where warnings matter. That is why we give it attention without giving it fear. And that is also why scientists who study this region are not laughing it off. They understand the baseline. They understand the probability. They understand the long-term hazard. They understand that one morning does not change the entire seismic future of the West Coast. But they also understand that the next major earthquake, whenever it comes, will begin as data before it becomes disaster. That is why they watch. And to understand that mindset, we need to talk about what seismologists are actually thinking when mornings like this happen. Not what conspiracy channels imagine. Not what panic posts claim. Not what dismissive headlines suggest. What the scientists are really doing is much more careful and much more interesting. Chapter 17, Why Scientists Still Watch Anyway. The easiest thing to say after a sequence like this is, nothing happened. No damage. No tsunami. No emergency. No major rupture. No reason to worry. And in one practical sense, that is true. But it is not the whole truth. Because scientists do not only study disasters after they happen, they study systems before they fail. That is why a moderate offshore sequence near the southern Cascadia margin still matters. Not because it changes everything, because it adds data to a system that already matters. Seismologists who watch Cascadia are not sitting around waiting for one magical signal. They do not expect the Earth to send a clear message that says, the big earthquake begins tomorrow. That is not how the field works. Instead, they monitor many signals at once. Earthquake locations, magnitudes, depths, focal mechanisms, aftershock patterns, tremor activity, slow slip, GPS motion, strain accumulation, tsunami modeling, historical records, paleoseismic evidence. No single signal tells the full story. But together, they help scientists understand how the system is behaving. When a sequence like June 3 happens, the response is not panic. It is increased attention. Scientists ask basic questions. Where exactly did the earthquakes occur? What faults moved? Were the events inside the Gorda Plate? Were they on a transform structure? Did any part of the main Cascadia interface slip? Did tremor increase? Did GPS stations detect unusual motion? Did the aftershock sequence decay normally? Are magnitudes increasing or decreasing? Is the activity migrating? These questions are technical, but the reason for asking them is simple. They are trying to determine whether the sequence is isolated or connected to a larger change. Most of the time, the answer is isolated. Most of the time, the system quiets down. Most of the time, the event becomes routine. But scientists do not know that instantly. They have to watch the data. And that is why the public sometimes misunderstands them. When scientists say, we are monitoring the situation, some people hear fear, others hear avoidance. But monitoring is not a secret warning. It is not a coded message. It is the normal scientific response to uncertainty. The problem is that earthquake prediction has a long and humbling history. For decades, scientists have searched for reliable short-term precursors, foreshock patterns, gas emissions, groundwater changes, animal behavior, electromagnetic signals, small crustal deformations. Some signals have appeared before some earthquakes, but none have proven reliable enough to predict earthquakes consistently. That is the key word, consistently. A signal that appears before one earthquake but not before the next cannot be used as a dependable public warning system. A pattern that works in hindsight but fails in real time cannot be trusted to evacuate cities. This is why seismologists are cautious. They know the stakes are enormous. A false alarm can cause chaos, economic damage, and public distrust. A missed warning can cost lives. And right now, the science does not allow precise short-term earthquake prediction. That is not failure. That is the reality of a planet whose faults are hidden kilometers underground. Cascadia is especially difficult because it has not produced a full margin rupture in the modern instrumental era. We have never watched a complete Cascadia magnitude 9 earthquake build and break with today's instruments. We have records from other subduction zones. Japan, Chile, Sumatra, Alaska. But every subduction zone has its own geometry, friction, fluids, sediments, temperature structure, and rupture behavior. Analogies help. They do not guarantee. That means the next Cascadia rupture will teach scientists things they cannot fully know today, and that is a sobering thought. The system is heavily monitored, much more than it was decades ago. Seismic networks are stronger, GPS networks are better, tsunami modeling is more advanced. Early warning systems can detect shaking quickly after an earthquake starts. But detection is not prediction. Shake alert can give seconds of warning in some places. It cannot give days. A tsunami warning center can evaluate a rupture after it occurs. It cannot tell you next week's rupture is guaranteed. GPS can show slow movement. It cannot always tell you whether that movement will trigger a major event. So scientists live in a difficult space. They know Cascadia will rupture again. They know the consequences could be severe. They know the region is accumulating strain. But they cannot tell the public when. That is why the honest scientific position sounds unsatisfying. The next major Cascadia earthquake could happen in our lifetime. It could happen long after everyone watching this video is gone. The probability in any given week is very small. The probability over decades is meaningful. Both statements are true. This is why events like June 3 are watched but not treated as alarms. They slightly sharpen attention. They do not rewrite the hazard. They remind scientists to check the system. They do not allow scientists to predict the future. That is the mature interpretation, and it is much more useful than panic. Because panic burns out quickly, prepared attention lasts. The people who study Cascadia are not trying to scare anyone. They are trying to understand a system that has produced catastrophe before and will produce it again. They are not hiding certainty. They are facing uncertainty. And sometimes uncertainty is harder to communicate than danger. Danger is simple. Uncertainty requires discipline. That is what this earthquake sequence demands. Discipline. Enough concern to pay attention. Enough restraint not to exaggerate, enough humility to admit what we do not know, enough seriousness to prepare anyway. Because the future Cascadia rupture will not care whether the public was bored by previous false alarms. It will not care whether people thought the science was too cautious. It will not care whether the last offshore sequence faded harmlessly. The fault will rupture when the physics allows it. Until then, scientists will keep watching the small signals. Most will mean nothing, a few may matter, and one day the signal will not be a warning. It will be the event itself. That is why scientists watch anyway. Chapter 18. The conspiracy wave that always comes after the earthquake. Every time the Earth moves in a way people do not immediately understand, another earthquake begins online. A wave of theories, screenshots, claims, connections, warnings, hidden causes, supposed cover-ups. And after a sequence near a famous danger zone like Cascadia, that wave can move faster than the seismic waves themselves. So before misinformation fills the space, let's deal with it directly. The first claim that usually appears is HAARP. Someone will say the earthquake was caused by a radio research facility. Someone will say directed energy triggered the fault. Someone will say the ionosphere was heated and that energy somehow traveled down into the crust beneath the ocean. It sounds dramatic. But the physics does not work. Earthquakes release enormous amounts of energy from stressed rock. That energy has been stored by plate motion over years, decades, centuries, or longer. A human radio facility does not have the energy, location, coupling mechanism, or physical pathway to reach a fault kilometers beneath the seafloor and force it to rupture. The scale mismatch is not small. It is enormous. The Earth's tectonic system is powered by planetary heat, mantle convection, slab pull, ridge push, and plate motion, not by a transmitter in Alaska. The second claim is solar activity. This one is more complicated because there is some scientific research exploring weak possible links between geomagnetic activity and earthquake timing. But weak correlation is not the same as causation. And causation, if it exists at all, is not the same as saying solar flares directly cause major earthquakes. For an earthquake to happen, the fault must already be loaded. The tectonic stress must already exist. The rock must already be near failure. Even the most generous versions of solar earthquake research do not replace tectonics. They only ask whether external electromagnetic or tidal effects might slightly modulate timing in rare cases. That is very different from the claims people make online. And for any specific event, timing matters. A solar flare seen on the Sun does not instantly mean geomagnetic conditions at Earth are storming in the crust. Coronal mass ejections take time to arrive. The Earth's magnetic response has to actually happen before anyone can even discuss a possible timing relationship. Most viral posts ignore this completely. They see two events close together and assume one caused the other. That is not science. That is coincidence hunting. The third claim is that the government is hiding the real earthquake data. This one also fails quickly. Earthquake data is widely public. The USGS catalog is public. Regional seismic networks publish data. Independent universities monitor the same events. International agencies also detect and report significant earthquakes. A real precursor signal strong enough to prove an imminent Cascadia rupture would not sit quietly in one secret office. It would appear across multiple networks. Researchers around the world would see it. The scientific incentive would be to study it, publish it, and warn about it if the evidence were strong. There is no practical way to hide a major regional seismic pattern from the global scientific community. What people often mistake for hiding is normal revision. Magnitude changes, depth changes, locations refined, solutions are reviewed. That is not concealment. That is how earthquake science works. The first answer is fast. The better answer takes more data. The fourth claim involves earthquake lights. This is where we have to be careful. Reports of unusual lights before or during earthquakes are not automatically fake. There is a real scientific literature on unusual luminous phenomena associated with some earthquakes. The proposed mechanisms involve electrical charge generation in stressed rock. But the key word is some. Earthquake lights are not reliable. They do not happen before every earthquake. They are not easy to verify. They can be confused with lightning, aurora, transformers, satellites, aircraft, meteors, camera artifacts, and ordinary atmospheric effects. Even if a strange light report is real, it is not a practical prediction tool. So if someone posts a blurry video after an earthquake and says, "This proves the big one is coming," be skeptical. Maybe they recorded something interesting. Maybe they recorded nothing unusual. Either way, it does not become a forecast. The fifth claim is fracking or injection wells. Human-induced earthquakes are real. They happen in some places, especially where large volumes of wastewater are injected underground. But those events have patterns. They occur near injection sites. They match industrial activity. They usually occur in regions with known induced seismicity. The June 3 offshore sequence happened far out in a tectonically active oceanic plate boundary system. That is not the signature of fracking. That is the signature of geology. The sixth claim is planetary alignment. Every time a major earthquake happens, someone will point to the moon, planets, tides, or some cosmic geometry. Tidal forces can slightly stress the Earth. That is true. But the idea that ordinary planetary alignments trigger specific damaging earthquakes in a reliable way is not supported. Again, the problem is scale and prediction. If planetary geometry could reliably identify earthquakes, it would work consistently. It does not. People remember the coincidences and forget the failures. That is pattern seeking, not forecasting. The seventh claim is that earthquakes are increasing globally because the planet is entering some new catastrophic phase. This claim feels persuasive because modern media shows us disasters instantly from everywhere. A major quake in one country, a volcanic eruption somewhere else, a storm system, a solar flare, a flood, a heat wave. All of it appears on the same phone screen. The human brain sees clustering. But global earthquake catalogs do not show a simple runaway increase in major earthquakes when properly adjusted for improved detection. We detect more small earthquakes today because we have more instruments. That does not mean the planet is suddenly cracking apart faster. The Mendocino region does not need a cosmic explanation. It already has one. 3 plates, a broken Gorda plate, a locked Cascadia interface, a transform boundary nearby. That is enough. The geology is already powerful enough. We do not need to invent hidden weapons, secret signals, or cosmic scripts. The truth is more serious than the theories. Cascadia is real. The Gorda plate is real. The triple junction is real. The long-term hazard is real. The uncertainty is real. And that is exactly why misinformation is dangerous, because it takes a real risk and attaches it to fake causes. Then people either panic for the wrong reason or dismiss the entire subject because the loudest claims sound ridiculous. Both outcomes are bad. The right response is to separate real uncertainty from fake certainty. Real uncertainty says, this sequence is probably routine but worth watching. Fake certainty says, This is definitely the big one starting. Real science says the event appears consistent with activity in a known active tectonic region. Fake science says a secret machine triggered it. Real preparedness says know your evacuation route and have supplies. Fake preparedness says decode random signs and wait for online predictions. The difference matters, because when the real Cascadia event comes, confusion will cost time, and time will matter. So after earthquakes like this, the best thing we can do is keep the story grounded. No cover-up, no magic trigger, no cosmic panic. Just a dangerous, beautiful, complicated coastline sitting beside a fault system that has moved before and will move again. That truth is enough. Chapter 19. The week ahead. 4 possible outcomes. So what happens next? That is the question everyone wants answered. And the most responsible way to answer it is not with a single prediction. It is with scenarios. Because the Earth has not given us certainty. It has given us a sequence. A moderate offshore quake. Several smaller events. A complex tectonic setting. No major damage. No tsunami warning. No clear foreshock pattern. From here, there are 4 broad possibilities. The first possibility is the most likely. Nothing important happens. The seismicity fades. The aftershocks become smaller and less frequent. The catalogue is refined. Depths are adjusted. Magnitudes are reviewed. The focal mechanisms are studied. A few scientific notes may be written. And within days or weeks, the sequence becomes another entry in the long earthquake history of the Mendocino-Gorda region. This is the outcome to expect. Not because nothing serious can ever happen here, but because most moderate earthquake sequences in active regions do not lead to major ruptures. They happen. They decay. They are absorbed into the background. The second possibility is also normal. More small aftershocks continue. People may see new dots on the map. Magnitude 2 seconds. Magnitude 3 seconds. Maybe more 4 seconds. This can look alarming if you do not know how aftershock sequences work. But after a moderate earthquake, smaller follow-up events are expected. The crust has adjusted. Nearby cracks respond. The system settles. Aftershocks do not automatically mean the situation is getting worse. Often they mean the opposite. They mean the sequence is releasing in a decaying pattern. The key is whether the activity becomes smaller and less frequent over time. If it does, that supports the routine interpretation. The third possibility is another moderate event. Maybe a magnitude 4. Maybe a magnitude 5. Possibly even something in the 6 range somewhere in the broader offshore region. That would get attention. It might produce stronger shaking on land depending on location. It might bring the story back into local headlines, but even that would not automatically mean a major Cascadia rupture is imminent. The Mendocino Triple Junction is capable of moderate events. The Gorda Plate is capable of internal earthquakes. The Pacific Plate boundary structures nearby can move. A magnitude 6 range event would be important, but not shocking for this region. It would raise attention. It would not by itself prove catastrophe. The fourth possibility is the low probability, high consequence one. A larger rupture follows. This could be on an adjacent offshore structure. It could be on the southern Cascadia interface. It could involve a more serious event near the Triple Junction. This is the possibility that people fear most. It is also the least likely. Based on the early pattern, there is no strong evidence that this is where the sequence is going. But low probability is not the same as impossible. That is why preparedness exists. Not because the most likely outcome is disaster, because the consequences of the unlikely outcome are so severe. If you live far from the coast, this may feel like an interesting science story. If you live in coastal Oregon, Washington, Northern California, or British Columbia, it is more than that. It is a reminder to check your basics. Not to flee, not to panic, not to cancel life, but to check. Do you have water? Do you have food? Do you have medicine? Do you have a flashlight? Do you have a power bank? Do you know where your family would meet if cell service failed? Do you know the tsunami evacuation route from your home, workplace, school, or favorite beach? Those questions are not specific to this one earthquake. They are specific to living near Cascadia. The June 3 sequence does not create the need for preparedness. It reveals whether preparedness was already there. That is the best way to think about the week ahead. Do not watch the map obsessively in fear. Watch the pattern calmly if you are interested. Look for whether the sequence decays. Look for whether magnitudes stay smaller. Look for official updates from real agencies. Ignore random predictions. Ignore countdowns. Ignore people selling certainty. Earthquake forecasting does not work that way. The most likely future is quiet. The second most likely future is small aftershocks. A less likely future is another moderate offshore event. A very unlikely future is a major rupture. The correct emotional posture is not terror. It is readiness, because readiness is useful in every scenario. If nothing happens, you are still better prepared for the real long-term hazard. If aftershocks continue, you understand them better. If another moderate event occurs, you are less likely to be surprised. If something larger happens, preparation matters. That is the logic, not fear, logic. The week ahead will probably be ordinary. The coast will probably continue its routine. Boats will leave harbours. Cars will move along Highway 101. People will go to work. Tourists will take photos of the ocean. The earthquake sequence will fade from public attention, but beneath that ordinary week, the deeper system will remain unchanged. The plates will still move. The Gorda plate will still deform. The Cascadia interface will still be locked, and the clock will still run. That is why the most likely future can be quiet and still not be comforting. Quiet is not the same as finished. Quiet is simply how Cascadia spends most of its time, until it does not. Chapter 20. What people on the coast should actually do. After a video like this, the most important question is not, should I be afraid? The most important question is, what should I do? And the answer is much calmer than most people expect. Do not panic. Do not evacuate because of this sequence. Do not believe anyone claiming they know the exact date of the next Cascadia rupture. Do not sit awake all night refreshing earthquake maps until every small aftershock feels like a personal warning. That is not preparedness. That is anxiety. The right response is simpler. Check your baseline. If you live in a coastal area of Oregon, Washington, Northern California, or British Columbia, you already live in a region where earthquake and tsunami preparedness matters. That was true before the June 3 sequence. It is true after the June 3 sequence. The earthquake did not create the hazard. The plate boundary did, so your preparation should not be dramatic. It should be practical. Start with water. After a major earthquake, water systems can fail. Pipes can break. Treatment plants can be disrupted, roads can be blocked, emergency crews may not reach every area quickly. Having stored water is one of the simplest and most important things you can do. Then food. Not gourmet survival food, just basic shelf-stable supplies that can keep you and your family going if stores are closed, power is out, or roads are damaged. Then medicine. If someone in your home needs daily medication, think about what happens if pharmacies are inaccessible for several days. Then light. Flashlights. Batteries. A way to charge your phone, a battery bank, maybe a small radio. Communication can become difficult after a major event. Cell networks may overload. Power may fail. Internet may be down. You need a plan that does not depend entirely on your phone working perfectly. Then family communication. Where do you meet if you are separated? Who is the out-of-area contact everyone can check in with? What happens if children are at school, one parent is at work, and roads are damaged? These are not fun questions. But they are easier to answer now than during a disaster. Then your home. Secure heavy furniture. Know where your gas shutoff is if applicable. Keep shoes near your bed because broken glass after nighttime shaking is a real hazard. Do not place heavy objects above beds. Small changes can prevent injuries. And if you are near the coast, know your tsunami evacuation route. This is critical. In a nearby Cascadia rupture, the first warning may be the shaking itself. If you are near the beach and the ground shakes strongly or for a long time, do not wait to see the ocean withdraw. Do not wait for a siren. Do not wait for a text alert. Move to high ground. Follow marked evacuation routes. Go inland and uphill. A local tsunami can arrive quickly. The phrase to remember is simple. Long or strong, get gone. If the shaking is long or strong, move. That advice matters far more than trying to interpret every moderate offshore sequence. Because when the real event comes, you may not have time for analysis. You will need action. That is why preparedness has to exist before the emergency. The goal is not to live in fear. The goal is to make the correct actions familiar. Panic happens when people face danger without a plan. Calm becomes possible when people know what to do. This is why earthquake drills matter. This is why evacuation signs matter. This is why emergency kits matter. Not because we expect disaster today, because we know disaster is possible eventually. The June 3 sequence is a reminder, not a command. It does not require you to change your life. It does not require you to leave the coast. It does not require you to cancel travel. It does not require you to imagine every aftershock as the beginning of the end. It simply asks a reasonable question. Are you prepared for the hazard that was already there? If the answer is yes, then keep living. If the answer is no, fix that quietly. No drama. No panic buying. No fear spiral. Just take the basic steps. The most prepared people are often the calmest people. They do not need every event to become a crisis because they already know what they will do if a real crisis arrives. That is the mindset coastal communities need, not fear. Competence, not obsession. Readiness, not denial. Respect, because Cascadia is not a movie, it is a physical system. And preparedness is not about predicting the exact day it fails. It is about accepting that one day it will. The June 3 earthquake did not tell us that day is here, but it did remind us that the system is alive. And if you live beside that system, the most powerful thing you can do is not guess the future. It is prepare for it calmly. Chapter 21. The modern test Cascadia has not yet taken. The Cascadia subduction zone has produced great earthquakes before. That is not the question. The question is what happens when it produces one now. That is what makes the next Cascadia rupture different from the last one. In 1700, there were people along the coast. There were communities. There were villages. There were lives changed and lost. The disaster was real. But there were no modern cities, no interstate highways, no electrical grid, no fuel pipelines, no high-rise buildings, no coastal tourism economy, no container ports handling global trade, no hospitals dependent on modern supply chains, no airports, no cell towers, no data centers, no bridges carrying thousands of commuters every day. The next Cascadia earthquake will not strike an empty coast. It will strike a connected one. That is the modern test. The earthquake itself will be geological, but the disaster will be social, technological, economic, and logistical. A major Cascadia rupture would test bridges. Some may survive. Some may not. It would test ports. It would test coastal roads. It would test emergency communications. It would test hospitals that need backup power, clean water, staff, supplies, and working roads. It would test schools. It would test small coastal towns that may be cut off. It would test evacuation planning. It would test how quickly regional and federal systems can move help into areas where normal access routes are damaged. And if a tsunami is generated, it would test the difference between knowing a route and actually taking it under pressure. This is why the Cascadia threat is not only about shaking. Shaking is the beginning. After the shaking come landslides, damaged roads, broken pipes, power outages, communication failures, fires, port disruption, supply problems, tsunami impacts, isolation of coastal communities. A major subduction earthquake is not a single event. It is a chain, and modern life is full of chains. Power depends on infrastructure. Food depends on transportation. Hospitals depend on roads, fuel, staff, and electricity. Phones depend on towers and power. Emergency response depends on access. When the ground moves violently across a wide region, those systems can fail together. That is why small reminders matter. Not because a magnitude 5.7 offshore quake is itself catastrophic. It is not. But because it points back to the system capable of producing a true regional test. The modern Pacific Northwest has never experienced a full margin Cascadia rupture. Not with today's population, not with today's infrastructure, not with today's economy, not with today's expectations of instant communication and fast rescue. Other parts of the world have faced similar subduction disasters. Chile, Alaska, Sumatra, Japan. Each event taught lessons. Each event exposed weaknesses. Japan in 2011 showed that even a highly prepared country can be overwhelmed by the scale of a major subduction earthquake and tsunami. Sumatra in 2004 showed how devastating a tsunami can be when warning systems and coastal awareness are insufficient. Chile showed the immense power of long subduction ruptures. Alaska showed how coastlines can change and waves can travel far beyond the source. Cascadia has studied those lessons, but it has not yet taken its own modern exam. That exam is coming someday. Not because of prophecy, because of plate tectonics. The plates are moving. The fault is locked. The geological record shows repeated rupture. The cycle continues. What we do not know is the date. That uncertainty can make people numb. If a danger has no date, people push it away. They say, maybe not in my lifetime, and maybe they are right. But preparedness cannot be built only around certainty. It must be built around consequence. A low probability event with extreme consequences deserves preparation. That is why emergency planners keep talking about Cascadia even when the coast is quiet. That is why scientists keep studying offshore sediments. That is why GPS stations track slow crustal motion. That is why tsunami evacuation maps exist. That is why schools practice drills. That is why bridges are retrofitted. That is why communities are encouraged to store supplies. The work is not glamorous. It is not viral. It does not make dramatic headlines. But it matters. Because when the test comes, the results will depend on decisions made during quiet years. Quiet years are when preparation happens. Not during the shaking, not after the wave, not when roads are broken, before. That is why this June 3 sequence, small as it was compared with the worst-case scenario, should not be wasted. It can become fear content, or it can become a preparedness reminder. Fear content burns attention and leaves people exhausted. Preparedness reminders build resilience. That is the better use of this moment. The coast did not suffer major damage. Good. No tsunami formed. Good. The sequence does not clearly point to an imminent rupture. Good. So use the calm. That is the gift. Use the calm to learn the map. Use the calm to check supplies. Use the calm to understand evacuation routes. Use the calm to respect the system without becoming consumed by it. Because someday Cascadia will not be calm. And when that day comes, the question will not be whether people watched the right video. The question will be whether communities used the quiet years wisely. The June 3 earthquake was not the test. It was a reminder that the test still exists. Chapter 22. Closing. The morning was a reminder, not a warning. So let's come back to where we started. Before sunrise. Dark ocean, sleeping towns, a quiet coast, a few instruments waiting in silence. Then deep beneath the Pacific, a fault slipped. A magnitude 5.7 earthquake struck offshore Oregon. More earthquakes followed near northern California. The map lit up near one of the most complicated tectonic corners in North America. And then, for most people, life continued. No major damage, no tsunami warning, no evacuation, no catastrophe. The morning passed. That is the simple version. But after everything we have walked through, you know the deeper version. The earthquake happened near the southern end of the Cascadia system. It happened in the world of the Gorda Plate, the Mendocino Triple Junction, and the offshore faults that surround one of the most dangerous locked boundaries in North America. It did not appear to break the main Cascadia megathrust. That matters. It was not the big one. That matters. It did not generate a tsunami. That matters. The sequence does not clearly look like an escalating foreshock pattern. That matters. But it happened in a region where the long-term hazard is real. That also matters. This is the balance. The event was probably routine, but it was not meaningless. It was probably not a warning, but it was a reminder. A reminder that the West Coast is not still. A reminder that the quiet beneath Cascadia is not emptiness. A reminder that the fault which ruptured in 1700 remains part of an active plate boundary today. A reminder that the Gorda Plate continues to crack, deform, and grind beneath the ocean. A reminder that the clock keeps running even when no one is watching it. And that is the phrase we should leave with. The clock keeps running. Not a clock with numbers we can read. Not a clock that tells us the day or hour. Not a clock that allows prediction. But a geological clock built from plate motion, friction, stress, and time. It has been more than 326 years since the last great Cascadia rupture. That does not mean the next one is tomorrow. It does not mean it is next week. It does not mean it is even in this generation. But it does mean we are living inside the quiet interval between events. And quiet intervals can be deceptive. They feel permanent. They feel safe. They feel normal. Until they end. The goal is not to live in fear of that ending. Fear is not useful over decades. Fear exhausts people. Fear makes them either panic or tune out. The goal is respect. Respect lasts longer than fear. Respect says the ocean is beautiful, but know the evacuation route. Respect says the coast is home, but store water. Respect says most earthquake clusters fade, but still understand the system. Respect says do not believe panic predictions, but do not pretend the hazard is imaginary. Respect says live your life but do not live blindly. That is the right response to June 3. Not panic, not dismissal. Respect. The morning gave us no dramatic images, no collapsed buildings, no flooded streets, no sirens echoing through coastal towns, just a few dots on a map, a moderate offshore quake, a cluster near the southern Cascadia world, a quiet reminder from beneath the ocean. And maybe that is why the story matters, because the Earth does not always announce important things loudly. Sometimes it speaks in data before it speaks in damage. Sometimes it moves where no one can see. Sometimes it gives a small pulse from the exact neighborhood everyone should understand better. Most of those pulses will fade. Most will never become more than catalog entries. Most will be forgotten. But one day the pulse will not fade. One day the locked boundary will finally give way. One day the coast will not sleep through it. And when that day comes, it will not matter who predicted it. It will matter who prepared. That is the human part of this story. We cannot stop the plates. We cannot unlock Cascadia safely. We cannot hold the Gorda Plate together. We cannot tell the Earth to wait. But we can learn. We can prepare. We can build better. We can listen to the science without demanding false certainty from it. We can reject conspiracy without rejecting concern. We can choose calm readiness over helpless fear. The June 3 sequence did not change the West Coast overnight. It did not start a disaster. It did not prove the big one is imminent. But it did something valuable. It made the hidden map visible for a moment. It reminded us that beneath the calm Pacific, the machinery is still moving. The plates are still grinding. The locked fault is still loaded. The broken plate is still cracking. And the coastline is still living beside one of the most powerful geological systems on Earth. So stay watchful, stay calm, stay prepared. And remember the difference between a warning and a reminder. A warning tells you to act now. A reminder tells you to be ready before action is forced on you. This morning was not the big one. It was not a confirmed foreshock. It was not a tsunami threat. It was not a reason to panic. It was a reminder. A quiet one. A dark one. A reminder from beneath the Pacific that the clock has not stopped. The coast moved in the dark. Most people slept through it. The map recorded it. The system kept running. And somewhere beneath the ocean, beyond the reach of our eyes, the next chapter of Cascadia is still waiting. The clock keeps running, and so do we.